Okay, so next, this is not 14 anymore, this is the old book, it's 17. Next is the process of dissolving is an important one to understand. So we're starting with a solid, and these solid particles are held together usually with pretty strong intermolecular forces, because otherwise it wouldn't be in the solid phase to begin with. Liquids are usually held together with pretty strong, not as strong, we'll call it moderate IMFs. If they were stronger, then it would be a solid. If it was weaker, then it would be a gas. So, moderate IMFs. In order to make these two things dissolve and look like the solution on the right, we have to overcome both the solute and the solvent interactions. We do that by having even stronger interactions between the solute and the solvent in the solution than they had with themselves before they mixed. Okay. So we can predict solubility. Here is some data. So if we just look at 0 degrees Celsius for all these lithium combinations. So lithium is in group 1, and fluorine, chlorine, bromine, and iodine are in group 17. And that's going down the periodic table. So there's a trend here. We're going down, which means the size is bigger as we go down. And the size of the halogen, the chlorine, fluorine, bromine, all that. Lithium's staying the same. And what we're seeing here is as we get bigger, as we get closer to iodine, the solubility is increasing. This is because when we think about lithium and fluorine, they're basically the same size, whereas lithium and iodine, lithium's pretty small, iodine is gigantic, right? And so if you think about how much overlap there is in these atoms, it makes sense that it's easy to rip apart the Li, because the lithium and iodine, because there's not very much of the iodine atom involved in the bond with lithium, so it's kind of a weaker bond. So if the intramolecular force is weaker, that means it's easy to split them apart. Lithium and fluorine are connected to each other a little bit better. They overlap more. So that means that they don't separate as easily, which means they're not as soluble, okay? You can also think of it as a polarity thing. This is going to be very, very polar in a way, because the iodine sort of has so many electrons. It's huge, right? So many electrons. So the trend here is that as the size difference between the cation and the anion increases, so the difference in size increases, the solubility also increases, because again, they're not as connected to each other. And you can see the same trend if you compare, well, let's see, if you compare lithium fluoride, sodium fluoride, and potassium fluoride, so the fluorine's all the same, we're getting bigger going down group 1 from lithium to sodium to potassium. You see that the solubility increases in a similar way. And again, that's because the size difference between potassium and fluorine is really big, but between lithium and fluorine, it's not that big a deal. So the bigger the difference in size, the more soluble they're going to be. Okay, so we can use solubility as a percentage. So we said that you can fit 36 grams of solute, if it's NaCl, into 100 grams of water. That's like saying that that's basically 36% soluble. 36 divided by 100 is like a percentage. So, like if you got 36 points out of 100 on a test, that's 36%. Okay, so that's a handy thing. So when I use that graph, I can think about it as a percent. And if I end up calculating anything less than 36%, then that is an unsaturated solution. Anything more than 36% would be saturated. Okay, so this formula sheet will be given to you for the test. It summarizes all the different concentration calculations that we have to do in this chapter. We're going to practice each one of these kind of in order here. So mass percent, the formula for that is the first one. It's the mass of solute divided by the mass of solution times 100%. So it says calculate the mass percent of NaCl in a solution prepared by dissolving 50 grams of NaCl into 150 grams of water. So the fact that there's 50 grams of NaCl and 150 grams of water tells me that the water is the solvent and the NaCl is the solute. So I'm going to put 50 grams of NaCl on the top because it said solute divided by solution. And now solution is a little tricky because it's solute plus the solvent. Okay, so we're going to go 50 for the solute plus 150 for the solvent. Don't forget to do this because if you don't, you're going to get the wrong percentage. You're going to be getting something that's more like solubility than mass percent. And those two things are not the same because solubility just had solvent on the bottom and mass percent says solution. Okay, so in the calculator, I put in 50 divided by 200, and we get 0.25, and then I multiply by 100, and I get 25%, and so that's our answer here. So what is the mass of sodium carbonate? This is carbonate because it's on the back of your periodic table, so if you don't remember what the CO3 is, you can look there. And so what is the mass of carbonate needed to make 350 grams of a 12.3% solution? Okay, so the equation is grams solute per grams of solution times 100. This equals the percentage, whatever it is. So this time they're giving us the percentage. So I'm going to just substitute it into this problem. So it's 12.3%, and it equals however many grams of solute, which we probably don't know because it's asking us for that. So grams of Na2CO3 divided by 350 grams, because this, it says 350 grams of solution, right? So I know there's a number in between. Don't let that confuse you. It's still 350 grams of solution. So we can put that one on the bottom. Okay, so to solve this, the first thing we've got to do is to get rid of the 100%. We're going to divide both sides by 100% to do that. Okay, so that gets us 0.123 equals grams divided by 350. And then to get rid of that 350, I'm just going to multiply both sides by 350. Okay, and so when we put that in the calculator, we get 43.05 grams are needed to make this solution. Those are the two kind of questions. We're either going to be having to calculate the percentage or we're going to have to use the percentage to find solute. That's pretty much it. Okay, so parts per million, ppm. That was grams of solute per gram of solution, again, times a million, parts per million. So a million is 10 to the 6. Parts per billion would be very similar, but 10 to the 9. So that's something to remember. How many parts per million of mercury are there in a sample of tap water with a mass of 750? Okay, so that 750 grams is the sample of water. So that's the solution, because tap water contains a whole bunch of stuff, including sometimes mercury, fluoride, chlorine, whatever's in there. So the 750 is going to be the solution. And then it says containing 2.2 milligrams of mercury. Okay, so that must be the solute. It's very small. Milligrams are way smaller than grams. Now, if I do this with milligrams, that's a problem because they don't cancel. I need these units to cancel in order to plug them into our equation. Okay, so we're going to have to convert from 2.2 milligrams by remembering that there's 1 gram for every 1,000 milligrams. So just like milliliters and liters. And so what that gives us is the fact that here I want to put 0.0022 grams. And now these two units will cancel. And so everybody's happy that way. And so I divide by 750 and then multiply that answer by 100. And we get, well, my calculator gives it in scientific notation, which is fine. I'm going to keep it that way. And it's a percent, so I'm going to put percent. Okay. Oh, no, it's not a percentage. Wait, oh, I did this wrong. Wait, back up. It's not a percent. We're doing parts per million, right? So we don't want to multiply by 100. We need to multiply by 1,000,000 to get parts per million. Ooh, that was close. Let's cross that one off. Okay, so multiply by 1,000,000, which is a 1 with 6 zeros after it. So that gets us 2.9 ppm. Okay, good. The next calculation to practice is mass per volume percent. So saline bags that you might use in, in the hospital or a nursing home, whatever, are made out of 0.9% NaCl, and they say M/V, so that means mass per volume. And so when we say that, it means that there's 0.9 grams for every amount of volume. In this case, it would be like 1 milliliter. So this percentage, you could think of it kind of as a ratio, just like we were sort of doing with the solubility before. The 1 mil is the 1 mil of solution, and 0.9 grams of the solute, NaCl in this case. All right, so in this problem, we're given the percentage, and we are what mass of sodium chloride. So we're trying to find the solute on top needed to make 50 milliliters of saline. So saline is the solution. So we're just going to plug it in like this. All right, and so again, we're going to divide by 100 first to get rid of the 100%, and then multiply by 50. And so x is going to equal 0.9 divided by 100 first, and then multiply that by 50. You can do that step by step. It's probably faster that way. And so our final answer is that we need to have 0.45 grams. This is grams because of how we define the formula of NaCl. Okay, so volume percent is milliliters of solute divided by milliliters of solution times 100%. So the percent equals this. There's a 6% by volume alcohol. They call it a soda, but there's alcohol in it, so, that happens. And so here the percentage is what we're starting with, and what volume of soda would contain 200 milliliters of alcohol. So in this case, the alcohol is the solute. I hope that there's more water than there is alcohol. So I'm going to put that one on the top, and I'm trying to find the one on the bottom. We're still going to divide by 100% first to get rid of that. And so we get 0.06 equals 200 milliliters divided by x. To solve for a denominator like this, we got to multiply by x to get it out of the bottom. And so we get 0.06x equals 200 mils. And then I got to divide by 0.06. So here x equals 3,333.33 milliliters. which is not a choice. This one's close, B is close, but if I convert it to liters, it would be that.